Hello everyone. I have had a couple of requests to go over one of the questions in this week's homework. I've gone ahead and reset it here. It is question 5 from week 1's assignment, section 5.1, which is due today. So this is a fairly challenging question. So I have a couple of other videos online in Canvas that go over this, where you just use the data that comes out of Desmos, but I'm going to show algebraically how to kind of get to that information. So let's go ahead and get through it. So in this problem, we have a radio transmitter that broadcasts a signal that is 53 miles across. So it's a circle whose radius is 53 miles. There is a city that is 71 miles north and a second city that is 72 miles east, and there is a road that is a direct connection between the two of them. So it is a line between these 2 points, if you would. And in that drive, we will actually be entering the transmission signal of this radio tower. So the question is, how many miles are we actually going to be able to pick up that that transmitter, the signal from that transmitter? Well, let's make a visual for it. The first thing we're going to have to do is we're going to have to identify this circle with a radius of 53 miles. And we're going to have the origin be where the center of that circle is. In order to get a 53-mile radius, we would have r equals 53 there. So our next thing we would need to do is we would have to identify our points. Now it says that there's a city that is 70 miles directly north, and then 72 miles is where a second city is. So if we were to look at that, we would have a city that is 71 miles north, and then a second city that is 72 miles east of it. Right, so if I go back a little, we'll see that this is the area we're looking for. So we have the 2 cities marked out here, and then we have our red circle kind of established that way. So we want to be able to represent the road now. We want to be able to connect those 2 dots together, so we want a line through that. So that's going to be some y equals mx plus b, where b is the y-intercept, so in this case it is at 71. And then in order to get the slope for it, we would just use our definition of a slope, which is the difference in y, so 71 minus 0, and then the difference in x, 0 minus 72. To keep it a little cleaner, I'm going to move that negative on the outside there. So now we can actually see the road when it moves through here. Now, the faster route would be to take the values that actually pop up in Desmos here and then use the distance formula on it. So the request is, how do you get these points? What do you do in order to find these things? Well, what you have in common between them is that is the intersection between the green line and this red circle here. So you want to know where these things equal. So in order to figure that out, algebraically what we would need to do is figure out what are the values of x and y that work for both of these, that make both of them true. In order to solve this, we would use our characteristics for different systems here. In this case, we're going to use substitution. So we're going to sub in what y equals for this line down here into this, into our circular equation, and then solve this thing for x. So I'm going to break this problem apart a little bit more now. We need to figure out what that squared is. So I'm going to move that down here. And then what we need from this is we essentially have 2 multiples of this. So I'm going to get rid of the x squareds and then just put them side by side. If we were to FOIL this out, we could see we're going to get 2 multiples of the 71 over 72. So if I were to break that off, I could get it here. And then what what I'm going to do is I'm going to have Desmos do all the heavy lifting for me here. Right? So, so in this case, I'm going to take my first part and put it right in there. So that's going to be 5041 over 5184. That's how many x squares I have in there. And then my outer and inner parts are where my x's are going to come from. So that is, I'm going to have two multiples of this 71 times negative 71 70-seconds. And that gives me minus 41 over, I have to go down to catch it, 36 x's there. And the last thing I need is I need to figure out my last term, so 71 squared. So that I'm just going to tag right on the end here. So that's how you figure out that part of it, right? So now we want to clean up this piece of it here. I want to combine my x terms together, so I have 1x squared plus this 5041 thing here. And if I were to combine those together, I'm again going to have Desmos do the heavy lifting for me. And I could see that this is going to turn into 5184. So that's how we take care of that part. We can see what we're doing is we're slowly making a quadratic function out of this thing. And in order to use the quadratic formula on this, what I'd need to do then is move this part over. So I would subtract, right, I'd have this 5041, and I would subtract 53 squared off of it. And when I do that, I can see that's going to replace this part with that when I subtract it over. So you can see what I end up when I substitute this linear equation into this circular equation is I get this quadratic result out of it. And if you remember from pre-calc 1, what that means is we will at most have two solutions for it, which are going to be the x values for where the circle and the line intersect. So I can use the quadratic formula for that, where a is going to be my 10,225 5,184. B is going to be negative 5,041 36ths, and then C is going to be 2,232. What's nice is I can actually get Desmos to reference all of these things. So I can write, say, the quadratic formula down here, and as long as I have everything kind of correctly identified, I should be able to get a result for it. And what's nice is it gives me the exact result. Even better, it goes through the actual point of intersection there. So as you can see, the answer that the graph gives me when I take my cursor over it is an approximation for it, whereas we can see in our actual answer over here, it's going much further. So that gives me my first point. And my second point, if you remember, would be where instead of going plus, we would subtract that over. So I can put a subtraction sign here. Now, in order to reference these things, because I don't want to have all this work now go to an estimate, I'm going to label these. If you take your cursor to the right of any variable in Desmos, you can assign it a value, so that way x sub 1 is a unique value for it. And just to keep it consistent, if I want to find the y value that's associated with it, I can plug it into either of these equations here. It makes more sense to plug it into this linear equation. So I'm going to plug that in right there, where instead of some x that I'm drawing from, what I'm going to do is I'm going to draw this specific x, this x sub 1. And then I simply need to repeat that process for y sub 2 to get the second point on it here. So that's how these points are found. And so if I were to go down, sorry, it keeps jumping around on me here. We can see here's our first point, right? This point that pops up right here, and then here's our second point. All of this, if you remember, is to make it so that way we can accurately define what the distance is between these 2 points. That is, when on this trip are we within that radio transmission signal. So that's going to be the distance formula, which is going to be the change in x squared plus the change in y squared. You can see that gives me the distance for this. Now, a good question would be like, well, is the long way worth it? How much more accurate is it? I've done this problem a lot of times because it is a fairly challenging question, and the last time I did it, it was off by 1,000th here. And 1,000th of a mile is, right, if a mile is 5,280 feet, would make that 5.28 feet. So it's about the height of, say, my oldest son. So, so that's pretty good considering what we're looking for here. I'm going to quickly write that down so I don't end up goofing up a decimal there. Well, actually, I'm going to try something. I'm going to try copying and pasting this. So I'm going to copy that, and then I'll jump over. And here's my moment of truth. Are. Okay, so again, this is a very challenging question. To be honest, this whole middle part here is the algebraic justification for it. But I feel that in Desmos, if you are accurate within 5 feet of this, then you did pretty good. So you can just take these points that come up off the intersection and then plug them into the distance formula. Again, if you have any questions, feel free to respond in the discussion page, or you can reach out to me directly. All right, I hope this helps, and I hope that you are getting through the term okay. Thank you very much.